we're starting by taking a look at adding and subtracting with unlike denominators just to bring it back, just because, we could use a refresher on it. So it's a little bit of an aside from all that logarithm stuff we've been doing. All right, now I want to start, for those of you who have struggled with this in the past, with just kind of a visual about what we're doing here. When we're talking about 2/3 plus 1/4, I can basically envision a whole and a whole, and I'm going to cut each of those up into their fractions. So for the first one, I got to cut it up into 3 pieces, and the second one, I got to cut it up into 4 pieces. And of course, 2/3 is 2 of the thirds, and 1/4 is 1 of the fourths. And we're being asked to add those together. So basically, if I take this chunk and I plugged it in up here, how much of it would be full? And then what number does that really represent? And so a way to represent that is actually putting the two together into one bar, but we still don't necessarily know how big that is. And so what you can actually do is visualize kind of carrying these lines down as a way to start cutting it up into some pieces. But even that still doesn't quite tell us. So how do I figure it out? Well, notice I can actually cut this whole big bar here up into 12 pieces. And by cutting it up into 12 in particular, I ended up being able to figure out exactly how much each of those is. And we'll talk about how we can find the 12 here in a moment. And so notice then how many total are shaded here. There's 11 of them shaded. Now, what is each one of those boxes? Each one of them is just 1/12 of the whole. So when we say something like 11/12, what we're saying is 11 pieces that are each 1/12 big. So really, that's what we're doing in order to figure out an answer of 11/12. But of course, we don't want to have to make a picture every time and try to figure out what that 12 is. It's challenging to do it that way. And so instead, we're actually going to do it arithmetically. So the first thing we want to do is we want to look for that common denominator. You always have to have a common denominator anytime you add or subtract them. For most people, the easy way to remember that is that you're multiplying the denominators by each other. Now, when you do that, though, anything I multiply the bottom by, I have to multiply the top by the same number. And so, if you didn't know what this answer was right away, you want to be writing down that work as we go as well. And so, when you do these, my big suggestion here that makes adding fractions with unlike denominators like this so much easier is actually write this out before you do the tops. Leave the tops empty for the moment because it helps you remember. What am I doing to 3 to get 12? Oh, I'm multiplying it by 4. So that means on the top, I'm going to have to be doing 2 times 4. And what am I doing to 4 to make it into 12? I'm multiplying it by 3. So I'm going to have to be multiplying the 1 by 3 as well. So we end up doing 1 times 3 there. It's a way to keep track of how am I getting that number on top. By putting the number on bottom first, it helps us to focus on what did I do to get that number on the bottom. And of course, the whole important thing is getting that same number on the bottom. A problem like this is one that we've done before, though, in here. Once we have the common denominator, of course, I can add them up. If I have 8/12 and I'm adding 3/12 to it, then it gives me a total of 8 plus 3/12. Each one of those is a single piece that is 1/12 big. So if I add 8 of them and 3 of them, I get 11 of them that are each 1/12 big. Same thing as we saw in the picture, but this way it's a lot easier to know. I got to cut it up into 12 pieces. So we can do the same thing with a problem like this as well. So for this one, what would be a good common denominator to use?
10.
10, absolutely. And so the first thing I write is I write my two fractions again, this time just something over 10 minus something over 10. The fact that this one's subtraction doesn't change this process at all. So what do I do to 5 to get 10?
2. Multiply by 2.
We multiply by 2. So I'm going to have to multiply the top by 2 as well. What do I do to 2 to get 10?
Multiply by 5.
We multiply by 5. So I'm going to have to multiply the top by 5 as well. And so we end up with 6/10 minus 5/10.
1/10.
And then, of course, I have 6 pieces and I'm taking away 5 pieces. And so that's going to leave me with 1 piece. And of course, each of those pieces is a 10th. And so we get an answer then of 1/10. Now I'm guessing that most of you have work that looks like this. You went ahead and multiplied the 6 and 8 to get 48. To know that's our common denominator, okay? And then that means I'm multiplying the top and bottom of my first fraction by 8, and I'm multiplying both of those by 6. And then I could go ahead and do the subtraction. I do 40 minus 24, which is 16, and then that's all over 48. But notice this is not my final answer, right? 18? Oh, sorry.
Wait, what? Okay.
Sorry, yes, thank you. That's not a 24 up there, that's an 18. Good. All right, get going too fast. Okay, so 40 minus 18 is 22. All right, so we got 22 over 48, but of course that's not done, right? We got to reduce that. And so notice I can divide top and bottom of this one by 2. Okay, so then that would give me 11 over 24. That would then be my final answer. And this work is perfectly fine. But do you see how you can actually do it without having to do quite as many steps? Because you may recall way back when you're doing all these fractions, people would always talk about the least common denominator. There's actually a smaller number than 48 that both 6 and 8 go into. What do you suppose that number is? Maybe the 24?
Yeah.
Because notice, 6 times 3 is 24, and 6 times 4 is 24, and 8 times 3 is 24. So I also could have done it this way. Now I'm not saying you have to do it this way, but it will save you a step. So if I turn them both into 24ths, I multiply by 4 there, so 5 times 4 is 20. I multiply that one by 3, and so 3 times 3 is going to give me 9. And so then I'm doing 20 minus 9. Notice in that previous one too, I was going really fast, and I made a multiplication error.
Yeah.
If they're smaller numbers, we're less likely to make multiplication errors as well. And so then I can go ahead and do the 20 minus 9 on top and get 11 24ths. Notice this also saved us the trouble of reducing it, because after I did that, it was already reduced. So it just makes life a little easier if you see that right away, but again, you still can do it the other way. It just always has to be reduced. So you're now going to be doing these 4. That way we can practice the adding and subtracting piece that we were just talking about, but also bring back the multiplying and dividing just so we don't forget them. Now, just to check in, when you're doing this, if you just multiplied our two denominators together, you'd get 18. If you went that route, this is the way your work would look for the first one. And then for the second one, it would look like this. It'd be the same basic idea. But is that the only way to do it? No. There's actually a way that you can do it a little bit shorter than this. So if you did it that way, yes, that's fine. Just remember to reduce. But I do like showing you some of the shorter ways that we can do it if we want to. And so what's the smallest common denominator you could have used between 6 and 3? You actually could have used 6, yes. 12, somebody said 12, that would also work. You could use that. And we could still use 18, but the smallest is actually 6. If you did it that way, notice you only actually have to multiply this one by 2 on top and bottom. And then when you do the addition, you get your answer already reduced. If you did it the other way, well, then you maybe start with 21 over 18. But then you divide top and bottom by 3, and you end up in the same place. So regardless of which way you did it, you should end up with the same answer of 7 6 for that first one. All right, and then for the other 3 here, the next one, it looks very much the same, except instead of a plus, it's going to be a minus between them. And so I get 3 6, which then reduces down to 1/2. So even though we used the smallest common denominator there, we still had to reduce. Sometimes that happens. For the multiplying problem, remember to multiply fractions, you just multiply straight across the top, straight across the bottom. We get 5/18. That doesn't reduce at all. And for dividing fractions, finally, that's the one where we multiply by the reciprocal. In other words, flip the fraction and flip it to multiplication. When we do that multiplication, then straight across the top, straight across the bottom, we got 15 6, which again, it reduces, so we have to reduce it to 5/2. Yes, if you turn them into a mixed number like 2 1/2, that's fine. I'm just not expecting that right now. We haven't talked mixed numbers, so I don't expect you to have to go there. The last thing we're going to do together here today is a little bit more practice on what we were doing yesterday. We're going to be solving exponential equations. So go ahead and write down this one and start solving it through, please. Now, as we're taking a look at this one, we always do want to try to get rid of any addition and subtraction first. So yes, I'm going to go ahead and get rid of that plus 30 at the start. So I'm going to subtract 30 from both sides, which gives me negative 2 times 3x equals negative 29. It's okay to have the negative there at the moment at least. But this is the critical step of this particular problem. I grabbed this one particularly because of this minus right here. I now still want to have the 3 to the power of x by itself. That means I want to move this to the other side. What am I doing to both sides? Am I adding, subtracting, multiplying, or dividing in order to move it? And that's the trouble spot for some of you at least. Because notice right now, it's negative 2 times 3 to the power of x. What do I do in order to undo multiplication? Dividing. We actually have to divide both sides by negative 2. A lot of us see that minus 2 and we think subtract 2. So we want to add it, but we cannot add it to get it out of there. We have to divide by negative 2. So do that and then continue doing the work from there. So when I divide by the negative 2, I get 3 to the power of x equals a positive 14.5. I now can go ahead and solve it for the exponent. In order to solve for the exponent, what do I always have to use? A logarithm. Exactly. And that's something I want you to kind of get really ingrained in your memory. Anytime you're solving for the exponent, we have to turn it into log form. Now, once I've turned it into log form, I need to be able to calculate that value. And for the vast majority of you, you can't just type that in your calculator the way you see it. We have to use the change of base formula, which, as you may recall, is where we write the log divided by the log. The question is, which one goes on top and which one goes on bottom? Yep. The one that we write lower goes lower. Or you could also remember the base goes on the bottom. And so it's log of 14.5 divided by log of 3. That's what you then type in your calculator to get your final answer here. And then the final answer, once it's rounded to the 100th, is about 2.43.